So I would like to open the floor to discussions. We have about 10 minutes discussion. If there are questions or issues that people want to ask or discuss, this is a good time.
There were a couple of questions that Kyle and Evan already answered, but if they want to elaborate, as people are typing up or raising hand, we can do that. Or I see Elnaz is up, so we can have her answer too. Elnaz, you can go ahead. Yeah.
Yeah, I have a quick question from Cecile and maybe Emmanuel. So you talked about using these boreholes and let's say surface wave testing to kind of get the characterization of the shear wave velocity, let's say. And I was wondering if you use that only to kind of come up with that stochastic model, or you also try to come up with a new near surface model as a 3D model to be on top of the existing model. So that part wasn't quite clear to me.
Yeah, so the answer is that we are using this geological borehole to derive the stochastic properties. We do not, the goal is not we cannot, and I think it will not be feasible to produce a deterministic 3D model that includes all the little variations. So we have in fact in the 3D model this macrozone. So a macrozone with gravel materials, a macrozone with clay dominated materials, and inside each zones we have some fluctuations that are described by this coefficient of variation and autocorrelation distances.
Okay, great, thank you.
So Manuel, I have a question. We all see that in the Grenoble Basin, we see that the duration of the ground motion, even for a small event, is extremely long. It's just like a magnitude 7 earthquake almost. So what do you think causes that? We all know that maybe, oh, sorry, the scattering is not going to really help you with that, but is any study about the quality factor or attenuation done in that area?
Yeah, yeah, you're right, Arben. The duration that Cecile showed, this is something that is really astonishing. So we don't have that many earthquakes to have systematic measure of lengthening of duration, but this example is really spectacular. And when the simulation that Cecile showed, they had some absorption properties in the synthetics that were probably not realistic. That is, at that time, and still now, we don't have a lot of constraint. And the constraint that were measured on the borehole is that there was no clear evidence of a change of quality factor with depth for the P wave. So we assumed that it was the case for S wave 2. And the simulation that you saw, in fact, use a constant quality factor in frequency, of course. I mean, as it is seen, but also in depth. And when you play with this, and when you try to basically increase the quality factor for the deeper part of the basin, then there is some, okay, you can increase the duration. So there is, as usual, a trade-off between you would like to you would need to probably fit those duration. You would need basically to have slower medium and maybe not too absorbing. So you have this trade-off between, if you have a, let's say, a correlation between the velocity and the quality factor, then okay, you will slow down some waves, but you will attenuate them more. So it's not clear. It's not clear. So I expect that the scattering, in this case, from the whole zone from the south of the basin to the borehole where it was recorded, I expect that with realistic correlation value curve value and all this distance, with all this lapse time, we may probably add some duration. But in fact, we realize that we are still quite far from having a realistic heterogeneous model. It's not as easy as we thought.
So my guess is that of course you guys are focused on the basin structure, but it sounds like based on tectonics, let's say the base rock structure could be really complex, and maybe the wave propagation scattering could be really a major factor that increase the actually duration of the input motion of the waves that are going into the basin. So it's not, we should not blame only just the basin, I think. That's my point. And so in that case, my question to all of you guys, based on your experiences, is how deep should we go with adding stochastic variability in in our modeling, and how well are those correlation lengths are constrained? Are we at the point where we can apply some of that at this time?
So just an answer, which is not an answer, Arben, but Hiroshi Kawase did some work with Eri Ito in Grenoble in order to improve the velocity structure in the bedrock. And definitely the bedrock that is used in the numerical modeling is too simple. So what was inferred by Eri Ito and Kawase Hiroshi will be put inside the next numerical modeling in Grenoble. That will, I think it will add something to the duration, but we are not yet ready to really look at the fluctuation in the fluctuation properties in the rock. And especially it will be difficult because we do not have so many earthquakes. So we have to find a way to get it or to measure it.
Thank you.
Yeah, just maybe one part of answer is for this event we have some recording on the rock. So it's like in the Mexico case. It's always difficult to really quantify the lengthening of duration and to attribute the part from all propagation, etc. What is sure is that I was quite amazed that in fact the parameterization of the fluctuation in the crust, basically with this fluctuation amplitude, the curve value of 5–10% maximum, this is working well. I mean, all the coda, this is explaining the coda, the envelope, etc. But if you look at the fluctuation that you can have in a basin due to, let's say, for example, in Grenoble to the river activity, those fluctuations are really much stronger. And what I'm saying today is that for the moment, we don't know how to model them.
Arben, David has a question. He has his hand up.
Oh, yeah, please, Dave, go ahead.
I know we're getting late. I'll try to make it short. I have two questions for Evan, so I'll give him both and he can respond. I'm curious, Evan, when some of this information may actually begin to be transitioned into the public USGS model for the Bay Area, if there's a schedule for that, and is that going to happen? Number one. And then number two, I'm curious how USGS thinks about these really soft sediments around the bay. When you get down to 200 meters per second or even lower, you know, you're probably getting in the soils are going to be very amplitude dependent in terms of their response and have nonlinear behavior. And what does the USGS think about the characterization of those? And is there a strategy that's different than other sedimentary deposits where the velocity is higher?
The first question, these updates to the model are not really on schedule to go into an updated version right now. We're still kind of playing around and deciding. We're just getting around to releasing the updated version of things, of all the changes east of the Hayward Fault. So I think once we get that finalized, and that's really the next thing on the schedule. And then you know, I know that you were at the last conference about the Bay Area velocity model. I think a big thing is, how often do we need to update this, and who gets to update it, and is there going to be some kind of repository? So this is me doing my own research. I don't know how we decide whether this becomes part of the model. I think we're not at that stage yet for this stuff kind of in the more urban area west of the Hayward Fault. East of the Hayward Fault, we're kind of ready to release the next update.
Okay.
The second question, I was a little unclear what you mean. What is USGS?
Well,
how do we feel about?
If you move forward on these velocities, I'm just curious, and you're going to assign some velocity structure to those. Would it be, in other words, would you be characterizing those soils without any thought or any recognition, I guess, to the fact that they could have significantly nonlinear behavior that could significantly influence, you know, ground motions? Have any comment on that, or would you just treat it like all the other velocity structure, or what might be your strategy there?
I don't. I'm not an expert on how those kind of nonlinear behaviors are usually implemented into these models. Actually, I mean, everything I do is in kind of the linearly elastic or viscoelastic in SW4. So everything that we're accounting for is like a linear elastic, but I mean, we could attach some kind of other property to points in the velocity model that account for nonlinear behavior.
Okay. All right. Thanks.
Oh, I have a quick question for Evan still.
Yes.
Okay, so you mentioned that in your model you have a minimum shear wave velocity of 250 meters per second, which I guess is mainly driven by computational capabilities.
Mm-hmm.
And I saw in your response to one of the questions that you also tried to run a model with a minimum shear wave velocity of 125 meters per second, without observing a just big difference. So I was wondering if the choice of going with 250 was just also given by just any sensitivity study that you did, and based on which you realized that, for example, that was the optimal shear velocity, or you think you can go like slightly higher, for example, 300 meters per second, or even higher, without really affecting the accuracy of your simulation results?
So the number 250 came from, you know, I know maybe Arvin and R.D. Rogers and a lot of people who are doing these kind of Bay Area simulations, we always say, okay, minimum speed of 500. And then we cut it in half. I said 250 now. So that's why I said 250. I think that, yeah, I think, you know, 300 might be okay. I think that what I was showing in my models, where you see these long, like kind of reverberations at around 0.8 hertz or so, I think it's less dependent on like the shallowest velocities, like the really, really low velocities, and more dependent on the contrast between the bedrock. So, you know, what's the velocity at, say, 150 meters? So that's why I'm comfortable cutting off the velocity at the surface, because I think I'm not going to the real high frequencies where I'm really resolving things at the shallowest layers where they get that low.
Okay, thank you.
So Evan, I have a question for you again regarding the, I'm muted, no, regarding the Bay Area model. So since you have done some simulations using small events, how confident are you with the model in terms of the frequency range, where we can feel kind of confident that our elastic modeling should be okay in the Bay Area?
So I think that, so the models that I showed today only went up to 1 hertz. I've tried models at around 2 hertz that also look pretty reasonable. I think that going back to what I said, I think the goal of the study that I showed today was to reproduce things that I saw at lower frequencies. I think if you want to get at the higher frequencies, you know, I've pushed it close to the limit of what I can do with that methodology, where I just fit curves and assign them all to whatever's based on the service geology. In the chat, someone asked me the question if, you know, I account for all these inner layers and stuff. So I think that that's very hard to do. I think at some point we can kind of set what I've done here for lower frequencies, and then we have to decide how detailed we want to get with adding these other layers, or should we turn to some kind of stochastic description to get the higher frequencies. So I think to answer your question in short, I don't know, maybe about 1 or 2 hertz is where I would say we've improved the model, but I haven't tried higher than that. And I don't know if we will get higher than that based on just the little, you know, changes that we've made for now.
Okay, thank you. Well, I guess, I don't know if there is another burning question of the discussion, but I think we ran out of time. Nevertheless, I think these are really very important talks and discussions, and I hope we're going to continue through other ways of communicating and keep those discussions open, and probably we'll have a follow-up workshop on more details on this. So I would like to thank you all, the presenters and the attendees, for this very fruitful session, and I look forward for the other ones, which are probably more exciting because they will involve more of the engineering community also. Thank you.
Thank you, Arben.
Bye.
Thank you.
Thank you.
Thanks, everyone.